Okay, super. Welcome, everybody. It's my pleasure to introduce today's speaker, Dr. Sunil Malik. So he's a postdoc here at UCM. You don't already know him. But Sunil completed his PhD in 2021 at the University of Delhi. And after that, he moved to Potsdam and Desi to do a postdoc for 3 years there. And he was a postdoc in India again, at the National Center for Radio Astrophysics from 2024 to 2025 until we enticed him to come here and do his research and tell us all about magnetic fields today.
Thank you, Sam. So today I will be talking about the magnetic field from small scale to the large scale, from planets to the galaxies. So before going into so before going into the small scale field, small weak field into the galaxies, I would like to highlight the magnetic field is very important in our daily life, starting from the Earth. So Earth have a magnetic field which is very important to deflect the solar wind, solar particles that we get from Sun. And Sun also have a magnetic field of few hundreds of Gauss, which is a bit higher than the Earth. And there is a very good regions between the Earth and Suns, which is blocked by the magnetic field of Earth. So this is interesting reason to understand all the turbulent phenomena happened when magnetic field, along with the cosmic, like the CMS, which is CME coming from the Sun, interacting with the Earth magnetic field, and then there is a turbulent region. So we can understand the turbulent in the space plasma. Now, if we go outside our solar system and look into our nearest star-forming regions and Orion Nebula, so we see the magnetic strength drop down drastically from the few Gauss, a few hundred of Gauss in the Sun to micro Gauss order. So here I'm just showing the different observations ordered on each other, and Planck 353 gigahertz polarizations, and there is these lines are basically denoting the magnetic field streamlines in the Orion. The strength is very important, which drastically decreases from few Gauss to the micro Gauss when we are going in the bigger scale. Now, if we talk the galaxy as a whole and see that what the typical strength in the galaxies, even if you average all across the galactic disk. So the strength is few micro Gauss, which is 1 millionth time of Earth. So our galaxies have a ordered as well as the turbulent field, and it can come from the seed field can come from the dynamo and amplified by different type of dynamo. So if we see some recent observation in the Milky Way, so I have shown these two observations. The above one is the Planck dust polarization map, and if we see that there are small scale turbulent field. I just highlighted one which is here. If we see that there are these regions are clearly showing there is a turbulent field, and there is a large scale field as well, and which can be probed using the polarizations of the pulsars. And here is the pulsar distributions, which is like black dots are representing the pulsars, and people try to understand the magnetic field using the rotation measures of the pulsars. So, if you go outside our Milky Way and look into some nearby galaxies, which we call it extragalactic systems, there is a magnetic field into those systems, and which can be studied using far infrared and other observations. So, since these galaxies are fairly very close by, and we can easily resolve, and we can clearly see that there are some kind of streamlines which is extracted or inferred from these higher polarizations observations. Now, if we see another of the nearby systems of M51, which is well-studied systems. So this is a picture which I'm showing is an overlay of radio emissions, and there are vector. The bars are denoting the B magnetic field, which is extracted from the polarizations of this radio flux that we are getting. and overlaid with the optical image from the HST. So we see this magnetic field bars are somehow following these spiral arms in the systems. So if we take the average, so the strength of magnetic field roughly coming few tens of microgauss in these galaxies. So now we know that the magnetic field is there, which can be a large scale coherent field and which can be a turbulent field. So this field can be decomposed into the average component and the turbulent component there. So the turbulent component can be divided further into based on the turbulence. So in briefly, this can be divided into alphanic mode and compressible mode. So which is nothing but decided by how the perturbations are propagating with respect to the direction of the mean field in the whole region. So this is the like perpendicular, the turbulent field is perpendicular to the direction of the magnetic field, and here it is perpendicular to the plane of this magnetic field. So this is basically just divided with respect to the direction of perturbations and mean field here. So people are trying to simulate this turbulent field and mean field in the MHD box and try to introduce some particle. Here is one example. So here, like these yellow lines are denoting the magnetic field variations in these cubes, and these small red dot are particle following this magnetic field and gyrating around those magnetic fields. So these cosmic rays in this in the Milky Way or in any dense environment are strongly affected by this turbulent field in the regions, which can be seen in any pulsar wind nebula or supernova remnants in our galaxies. So now, how do we study these magnetic fields? So we know that these magnetic fields are there. They are important, turbulent as well as the large scales. So here's a brief list of probe magnetic fields. Some of them are direct probe, some of them are indirect probe. So direct probe where we can directly have the observations and which can directly represent the magnetic field strength. So one is the Zeeman effect, where the molecular line is basically splitted based on the magnetic field strength and the temperature of the gas there. So the condition to have the Zeeman effect is magnetic fields need to be very high. So and temperature of the molecular cloud should be low, so that the Doppler broadening should not be dominating these Zeeman splitting. So these conditions allow us to probe the magnetic field in the molecular clouds using the Zeeman effect and in some nearby systems. So the other is the polarization of starlight by the dust, which is basically the elongated and rotated dust with non-zero magnetic moment. It can polarize the light from the background stars and can give an influence of the magnetic field. So other is the Faraday rotations. So other is the Faraday rotations, where the rotation of the plane of polarizations of linearly polarized light when it passed through the magnetic plasma. So then that people observed these rotations and infer the magnetic field, and the synchrotron radiations, where we observed the polarized radiation coming from the the relativistic particles, and then we infer the magnetic field. There are some indirect one as well, where we observed the scattering and the time delay in the gamma ray observation from the blazars, and try to get a strength of magnetic field in intergalactic medium using these two probes. Another is the CMB observations, which is again like people are using bispectrum, trispectrum to constrain the early universe primordial magnetic field. Now, just to summarize these probes, these are the probes. Basically, we need relatively charged particles. Here we need magnetic plasma, cold gas, elongated dust, and these are observable. So there is another further divisions that where we can use. These are the local probes, Zeeman splitting, dust, and Faraday rotation from the pulsars. And then if we go to the high redshift, these dust and Zeeman splitting won't work. So we need to rely mainly on synchrotron if there is a radio galaxies. And if you want to go deeper in redshift 1 or so we need to rely on the Faraday rotations of the quasars light when we pass through the galaxies. Now, using one of the probes, Faraday rotations, I will be discussing how we can probe the large scale field in some high redshift galaxies. So just to get the detail of the Faraday rotations, here the synchrotron polarized light, which is coming from a given extragalactic sources, when it passed through the magnetized plasma, so there is the rotations. The side was the initial plane of polarizations. When it passed through, it becomes psi. So it depends upon these two factors: the strength of the parallel component of magnetic field and the number density. And here, this number density of electrons are the thermal electrons, not the non-thermal non-thermal one, which can be a relativistic one. So we need the thermal electron density separately to extract out the magnetic field using RM. So here the light is divided into two parts: left circular, right circular, and people observe this polarization plane based on two wavelength. And at least if you have these two points, so you can easily get the RM from these observations. But there can be a pi rotation degeneracy or ambiguity. So to break that, we need at least 3 wavelength observations to break the degeneracy. But 2 can also be sufficient to get the rotation measures. So this is how we observed in the real scenario. Now, in first projects, so we are using quasar as a background source. So we have two type of quasars. In type A, where there is a foreground systems is there, foreground galaxy is situating, and in type B, there is no such system is there. So these quasars should be radio loud so that we can have the polarized properties. To detect there is some foreground system or not in the foreground of these quasars, we need to rely on optical observations. So radio observation do not have any significant way to estimate that like there is some object sitting in along the way, until unless there is some additional radio emission from these individual objects. So for that we have used optical observations and radio observations simultaneously from two different telescopes. So for the optical observations of the optical spectra, we use MG2 doublet line as a precursor, as a proxy to identify these intervening galaxies. So there is a difference in the RM. So RM was the rotation measures is contributions from the several objects. So if we start from here, so there can be some host galaxy contribution, which we are calling it a RM intrinsic, which can be there in source B. So there will be a Milky Way contribution in both the cases. So the line of sight pass through the Milky Way, depend upon the direction of these sight lines. So we have the GRM component in both these systems. There will be a IGM contributions which will be there in both the case, except that there is an additional contribution in source A, which is RM intervening, which we are saying it is contribution from these individual galaxies. Since these two observations are from two different facilities, so the resolution for these optical and radio can be different. So we need to make sure that we are observing the same object. It is generally a quasar. It is easy to confirm that it is a quasar in optical. So, but in radio, we don't have specific feature except saying that there is a radio loud quasar, if we know that. So we cross-match these two catalog and we put some another criteria of redshift based on the SDSS coverage. So with the positional cross-match of 7 arcsecond, we find that we can make sure that these are from the same source. Still, there are some ambiguity about this proximity radius that we are refining in our with the better observation for the radio. So with these cross match based on these selection criteria, we find there are total around 1135 systems. So we have given different priority to these different catalogs. So we find that total 1135 quasars are there, which are having foreground informations. Out of these systems, out of these 1101, we have very few of them, around 350 sources, which are there with the foreground MG2 observers. So there can be multiple observers along the way, not necessary to be only one intervening galaxies. So we have some of the systems which are even more than 2 observers. So for identifying these observers, we use the existing pipeline classification for these quasars. and that was done by these different people. But when we check visually for these MG2 observers, we find that the automated classification is not accurate. So there is 8% misidentification from the pipelines. So we find that some of them genuinely are missed. Some of the noise are considered as MG2 lines. And finally, we rely on this visual check of this the classification, and 352 sightlines are there. There is a foreground galaxies and 780 without one. Now we have to remove the Milky Way part individually because there is a directional dependence. So we have used a galactic rotation measure Milky Way map from an existing catalog, and we have removed these galactic contributions and left with the residual rotation measures or RRM. That is the final parameter that we are propagating for further analysis. So this effect of subtraction of Milky Way contribution is also clearly visible. So mean is clearly shifted from 5 to around 0. So there is a genuine shift, and which is also the width is also reduced from 20 to around 15. Now we have to see that what kind of statistics that we can employ on these RRMs. Can we assume that these individual observations can belong to a Gaussian distribution? So when we looked into the distribution of RRM, and we find there is a fairly a Gaussian in nature, and even if we classify the absolute values, and it increases with the Gaussian in nature. So the Gaussian estimators can be used here. Here is the histograms for these MG2 observers, and these galaxies are spread up to 2.2 redshift. So we are generally going into the high redshift range. So this is the distribution for the observer sightlines. This is with the combined one. This is with the observer redshift. So we have used the Gaussian approach, the Gaussian estimator. So starting from the standard deviations for these sightlines. But the standard method of RMS method is affected by the outliers if there is a present in the system. So we have used the MAD method as well to remove the outlier effect. And we have these two subsample. We are interested only in the contribution from this intervening galaxies. So we have to subtract them coordinately. So we can do it using the Gaussian assumptions and propagate in the air. So now if I just directly show the results. So here there are this axis is from these intervening galaxies. So there is an 8 radian meter square contribution from those intervening galaxy systems, which is like axis. It is also in the RMS case, but with the higher error bar a bit. So the sigma for these one are highly affected by outliers. So which we can clearly see, which is less here in MD and which is higher in the RMS case. So we were initially interested for the magnetic field, not just determining how much excess contribution is there from in the RL. So we have to propagate, we have to translate this excess spread or excess RRM from this galaxy to the magnetic field. So we have just play with that initial formula of how the RM depend upon the magnetic field, and we have to assume some assumption for this electron density. So we have taken from archival that this approximation for the electron density, and find that magnetic field is roughly of 1.3 microgauss, which is fairly similar what we observed in the nearby local universe. So at least from these observations, we don't say that there is much of the evolution, but still we need far more detailed study to say that if there is any magnetic field evolution in this galaxy or not. So this was just to combining all this study. We looked into the data again, and we try to think that if we can develop some radial profile of magnetic field into these systems. So we looked into our data again and find if there are multiple observer sightlines and there is only single observer sightline. So we looked into it, and if we want to classify what is the impact parameter of these quasar sightlines based on the center of the galaxies. So we find some 59 systems very fairly close. We are only going up to 0.8 redshift, because to identify the impact parameter we need photometric observations to see in the image how much the separation between the center of the galaxy to the quasars. Here is some couple of images from the SDSS finding chart. So we clearly see that there is a different separations from these galaxies. So we have such 59 charts, so we can easily determine the impact parameter. And here is the impact parameter histogram for the sight lines. So we have sight lines mainly from outside the disk, from the 19 kpc or to the 20 kpc to 160 kpc. So we are mainly probing the magnetic field in the CGM, not in the disk part. That is clear from these impact parameters. So when we look into the subset where there is a sight line passing through the less than 50 kpc and greater than 50 kpc, we can clearly see the CP, there is a significant difference. So we looked into the distributions of the RRM. I think, but do you have another one? Yeah, the battery is gone. Okay. Yeah. So when we divide the data into beam, and we can clearly see there is a spread, and this is the sigma or the spread. There is no observer, so we have to determine the excess in every set. We have to subtract them quadrilaterally, and so we have done that, and we find this excess, and this excess is decreasing as we are going away from the galactic disk to the CGM, which is expected. So when we in any normal galaxies, so the magnetic field should decrease, and when we translate, assuming the electron density throughout these radii, so magnetic field is decreasing from 2.4 to around 1.8 or so. So this was one of the attempt, but this study is highly dependent upon this assumption of electron densities, which is can be a very crude approximation. So we questioned these approximations, and then we thought, can we use some observations to develop the radial profile of the electrons, and which need to be the thermal electrons. So we looked into the archive. When we was going through the probes, we find that the S2 and O2 observations, So S2 and O2 observations line or doublet lines, which are coincidentally excited lines, can be sensitive to the electron, which can be a thermal in nature. So we looked into these observations for S2 and O2, and the manga is a good sample to look into. We looked into the full manga sample. To reduce the projection effect, we limited ourselves with the inclination angle of the galaxy to be less than 10 degree. So when we are putting the condition of 10 degree, so from the 10,000 sample of the manga, we end up with the 28 system only. And we have removed some of the systems based on the flux coverage, because these systems might have some of the hole in these observations. These are the map of S1, the first line in S2 and then second line in S2. So this is one of the good picture I am showing with some interpolation in the flux. So when we are looking into those 28 systems, there was a significant amount of hole available in these flux. So we have put a condition that the flux coverage should be more than 70% to consider this system in our analysis. So we left with only the 13 systems where there is 9 are star forming galaxies and 4 are non-star forming galaxies. So out of 10,000, only 13 systems were there which are good to utilize. So we estimate the electron density based on the existing literatures, where these constant can depend upon the type or morphology of these galaxies. So here we are combining all these systems, so ABC can be different for these individual 13 systems. Since we are doing the statistical study, we thought, okay, let's try to combine them. And we draw the different annulus and estimate the LE. And when we looked into these distributions, we find there is a decrease when we are going from the center of the disk or the bulge part to the outer side of the disk. So we combined these systems and we estimated the electron density, and it is clearly shows the decreasing trend in all star forming and non-star forming systems. So still the statistics is poor, so we have only 13 systems. These trends can be questions. We are still working on it. We are trying to increase the inclination angle to 15, where the statistical sample can be significantly increased, and now sample is becoming 66 galaxies out of 30. So the trends is remaining same, so I am not showing those results, but then the projection effect can questions if we are increasing the inclination angle. So here we are going up to only 18 kpc or so. So if we want to utilize this density variations into the magnetic field study, we can't still use it because our sight lines were starting from 20 kpc to the 160 kpc. So here we are just probing only up to 18 kpc or so. So, but we can check that the approximation that we used in the beginning in earlier to work of 10 to the power 20 can still valid or not. So when we are looking into it, this value is going up to 10 to the power 22 or so at the 18 kpc. So the assumptions for the impact parameter higher than 20 kpc of 10 to the power 20 can be fairly okay. So these approximations, but we have to be very careful the impact parameter to utilize the electron density. And this is what like the approximation that we have used. So this approximation is not that bad. So this was the first part. So I have the second part. If there's any questions, so I'm happy to take it at this stage. Yeah, because now I'm jumping into the small scale table.
Yes, that's a good question. Is there any impact that the filling factor of the ionized gas could have if it's, because I assume you are assuming here that it's 1. So
yes,
if it's not 1, what would be the impact on the how that translates into the rotation of the?
Yes. So if the sight line is passing through very dense environment, and but that dense environment should have the thermal electron. Yes, it can definitely affect our observations. But how do we account for it? So we have to determine we have to have some IFU observations to see that these are the high star forming region there, and we have to either remove those sight lines if you are making statistical study, or we have to be saying that this contribution is only from this bulky regions which is sitting along the way, not from the whole disk. So we cannot claim this RM axis is from the integrated of the whole regions. It could be dominated by those both.
But if locally was that you are in a region that you see that is fully ionized, but if you have inside that H2 region or H2 complex, some neutral and ionized region, will that still impact?
Yes, it will impact our studies definitely, but we don't know how to account for as of now. There are some systems that assuming these foreground galaxies as an inhomogeneous screen, and people are developing some theoretical model to say that if we can use the wavelength as a third axis and get the polarization versus lambda square, so that we have a different peak at different lambda. So we are kind of probing the depth of these intervening galaxies. There we might be able to break these analyses. Yeah.
Okay, when you saw the gradients of the magnetic field, you said there was a decreasing, it was decreasing with radius, but it was pretty flat the text for the innermost point. I mean, what I see is that
there's no degradation. Yeah. So this is basically because when we are going higher, the sight lines are very less. Statistics is affecting our analysis. So better would be, I think, doing the rolling. We have not done the rolling sigma, so we should do that. We will see that. But yes, the error bars are very large again because the RM observation that we are propagating into the magnetic field, initially they are from very old observation from the VLA. Now with the latest result from the OSM survey, we have very good accurate RM, and this profile that we will hopefully next year we will have another set of profile with very short error.
And that is a little bit related to work, but what is ionizing the gas in the non-star forming galaxy?
Yes, so we don't know. Generally, we don't know. So
because it's at large distance. I mean, in the center you have an engine.
Yes, in fact, it's this one even higher than the star forming one. This is the non-star forming one, which is from O2. So we don't know. Maybe the we are questioning the classification as well. So the classification of and some of the grain valley is also in the non-star forming. So we have to be very careful. Or maybe there can be some Asian which is misclassified, which can also affect these regions. So these are the possible regions that we are accounting. But we are like just combining only 4 systems are here. But in the when we are including the inclination angle of 15, the system becomes 26. There we are being more careful that removing the Asians and all those things. So now coming to the small scale and turbulent field. So we again, in going back to the full list of probes, can any probes suggest how do we estimate the mean field inclination angle in these systems and the turbulent characteristics? So we thought the synchrotron anisotropy, when we observed, can have some 3D directional informations and the turbulent properties of the magnetic field in this system. But these synchrotron observations should be in very high resolutions, and it can be possible only for our Milky Way. So first we tried to develop this technique in the simulation. So we did the simulation of these synchrotron radiations in generating a cube with MHD plasma and putting some seed field, and there is an external field as well. So this is a schematic diagrams where we can easily produce the polarization vectors, and we have handled over the magnetic field distribution in every slice of these simulations. And this is just a cartoon diagram how the polarizations can be different for the different inclination angle. Using this approach, we have simulated the IQU, or these are the observable in any synchrotron observations, and we produce for the whole cube with the different parameter of different injection length scale, different type of turbulent there. I'm just highlighting this last column here, which is a C mode energy fraction. So when we are developing a MHD turbulent cube, we can control how much energy is going in which mode. So based on the initial distributions. So the C mode energy is varying from 18% to the 91%. So when the C mode energy is low, so these are basically the alpha mode dominated cubes. When it is higher than 50%, it is the compressible mode dominated cube. So these are generated using the two different package which is publicly available, this and Etna. These are the 3D simulations. So we have developed this criteria based on the anisotropy of I plus Q observable. So I plus Q is like our observable. Here I is the polarized intensity, and which is proportional to the Bx square component. And I minus Q for y, and we taken the relative anisotropy of the correlation functions, which is a global correlation function. And this is the dimensionless parameter that we developed, and we have tried the other possible combination of I plus Q as well, but like variance of I plus Q instead of taking the correlation function. But this Y parameter with the anisotropy of correlation function is giving the good result. So this is the correlation function distributions which is there for A mode. This is one of the cube which I am showing is a Z12, which is just A12, Z12 is the 24% compressible, so alpha dominated cube. So the another one which I will show the A1, which is basically 84% C mode, so it is a compressible dominating cube. When we looked into the Y parameters, which is estimated based on the correlation function distribution, so I'm just showing the correlation function distribution for 0 inclination angle and this 90-degree inclination angle of the mean field with respect to the line of sight of the observer. We find that the Y parameters is decreasing for the A mode from higher to lower and converging towards around 1.5, and it is increasing for C mode. And here on x-axis, this is the inclination angle of the mean field. So here we see there is some trend coming up for this parameter. We have repeat this analysis for all these 25 cubes, and here for the A1, for the decomposed case, it was showing the similar trend. But when we are combining this, it is also giving the decreasing and increasing trend. Here the color are denoting the probability distribution, and cross is representing the median value among those 12 cubes and in 8 cubes among these compressible dominated. Now, in reality, we are in sky when we are observing the synchrotron either from the supernova remnants or from the ISM. We don't observe the decomposed case. We observe the total B field which is responsible for the synchrotron. So we have to see that how does the trend look like for the total field. So in this case, total field, since it was an alpha dominated cube, so it should follow the decreasing trend, and it follows the decreasing trend. And in case of A1, it has an increasing trend. So this was the decomposed one. So the total one should follow the upper one, and it is more or less following it. And in case it is following the downward, which is C mode. So based on this approach, and here I am just combining the statistically for the total cube. So if we see the y parameter versus theta lambda for all the 25 Qs, we can clearly demarcate that it is higher for the in the lower theta lambda for the alpha case, and it is decreasing for in the initial case for the compressible case, and it's like other way around. So we design this flowchart where we have the synchrotron from any object like from the ISM or supernova remnant from with a very good high polarized telescope. We can easily produce the y parameter and we can put into the three different category and see that where our y parameter is lying. And there are regions which is ambiguous region where we don't know what it is. So the value converging was 1.5. So between 1 and 2 we are putting in the ambiguous range. We have used this approach into the couple of sources. One is in pulsar nebula, supernova, the supernova remnant Cygnus loop, and using other two as well. I'm just showing the one in here. So the motivations to probe this turbulence in the pulsar nebula is recently there was some tera electron volt observation from the two of these nearby supernova pulsar nebula, which is Geminga and Monogam. So they are very close in the sky as well as from the distance from us. So Geminga is around 200 parsec from us. So because of the close proximity, we can even have a very bad resolution telescope giving us a reasonably good high observations. So we have the archival observations from the Effelbergs, which is 10 arc-minute observation. Since it is very close by, we can go into the smaller scale. And this turbulent is important into the explaining the tera electron volt observation that people are getting from these two telescopes. So existing astrophysical phenomena was not able to explain that. So in my earlier group, these people invoked theoretically the turbulent phenomena and justify the spectrum in that GeV range or TeV range which they were getting for these telescopes for these sources. So when we looked into the monogam, we find some archival observations, and here is the polarized intensity map which is shown, and we can clearly see there is some high excess polarized intensity around the center of this region, and where the center there is a pulsar, monogam pulsar is also located. But in real observations, it is confused that which scale we have to probe. So we have to estimate that we are in a turbulent regime, not in the coherent or homogeneous region. So we looked into the structure functions of the polarized intensity, and when it is saturating, we are in a coherent regime or the large scale field. But when it is increasing, so this region is basically the turbulent region. So we have to use this scale to estimate the y parameter from the real the polarized intensity for this observation. We have done this, and we find that y parameter for this monocam pulsar nebula is 0.83, which indicate that the region is dominated by the compressible mode, not by the alpha mode, and which was the predictions from the theoretical these studies where they were suggesting that the compressible mode can accelerate the particle and justify these tera electron volt observations. So we were getting the theta lambda or the mean field inclination in the regions less than 10 degree, which is again the theoretical expectations. We use this technique into the another region of Cygnus loop, which is very complex morphology supernova remnant. It is not clear is it a single supernova remnant or merging of two supernova remnant. So this we have divided this region into the three regions: southern, central, and northern. Here I am just showing the 11 centimeter observations. They are like fairly good resolution. It is at 4 arc minute, better than the earlier one. And we have repeated. We have the other observation as well, like 6 centimeter one and 23 centimeter one. But this technique needs good resolutions as well as the Faraday rotations should not anisotrope these synchrotron observations for this particular region. So we are relying on only the 11 centimeter, not on the 6 centimeter and 23 centimeter. So we repeated the analysis which we did for the pulsar PWN, and we find that these two regions, southern and central, have a similar morphology, and in both the cases, the compressible mode is dominating, and in the northern one, there is an ambiguous region based on the y parameter observations. So with this, I will come to the conclusions. So we have the galaxies do have a magnetic field, large scale, small scale, both of them, and both are very important in their own region. So now magnetic field, when we are going from the disk to the cesium, it's decreasing, but how much it is decreasing, that still need to probe with better observations. Electron density plays a significant role, and we need more better result for electron densities, particularly how it decreases when we are going in the cesium regions. So in the disk, still the IFU observations are very good. Even in the disk, still we need better probe. The distant one is not the reliable one. So we developed this technique to probe the turbulent field, which can be utilized even in galactic plane, in galactic center, in supernova remnants, in pulsar nebula, and can be useful for the particle acceleration model, and can justify the GV and TV observation that we get from these regions. Thank you.
Okay, thanks very much, Sunil. So, yeah, question for any part of the talk, I guess. Maybe I can start by just asking, so for this turbulent field where you're discriminating between this compressible and alphanic mode, so for supernova remnants, is it kind of theoretically understood which one should dominate?
Not necessarily, because not all the supernova have GV observations. Very few of them are emitting in giga-electron volt, and nobody knows what is the reason. Is it a shock, or is it the turbulent field? Why there is a high energy emissions?
It's
so
a diffuse gamma ray source,
yes,
not
it's
the pulsar.
yeah. So if you see the extension of this, yeah. So if you see this regions is going up to 50 kbc or 50 parsec. So it is not just a center. So this is the diffuse one, and there is the profile is properly decreasing as we are going. So if in terms of degree, it is going up to 10 degree. So this is not from the point source. So it is definitely in the pulsar nebula regions or around surroundings, which is dominating.
And to accelerate these particles, you need to know what phase or what the
yes. So if you people theoretically in the simulation they try to put the alphanic turbulence, and particle was not it also depends upon what is the particle model you are putting in. So even after increasing the particle energy, it was not the resonance was not happening. So it was not getting accelerated. So they invoked that compressible one and found that they are justifying the spectrum.
Questions online, maybe?
Yeah, they can just unmute themselves. There's a question in Zoom. You can just unmute and ask your question because the speaker will hear you.
Okay, well, we can take another one.
I think Ramon has one.
Okay, so now you have the first cosmological aerodynamic simulations, including magnetic fields.
Yeah.
You have to check if, for example, the trend that the magnetic field was decreasing from the galactic disk to the CGM is also reproduced in the simulations.
Yes, in fact, not the cosmological one are taking one galaxy out of the cosmological one and assuming the cosmological simulation have a significant impact on those smaller scale. For galaxy is an individual point object for a cosmological case. So there, it will not be a good idea, but people have done the individual simulation for individual galaxies, and the trend seems is decreasing. So there, people are going up to 1000 kpc. So it's clearly decreasing. So it's again in debate, people, do you assume the cesium to be at the 1000 kpc or at 500 kpc? So we are going up to 180, 160 kpc, which is fairly decreasing.
And maybe the magnitude of decrease. So you showed the RM radial profile.
Yes.
Did you have a magnetic field?
Yes,
radial profile.
Yes, we drive it assuming the constant electron density. Yeah. Yes, so we have access and then propagate into the loop.
Right.
And here the only difference, like it will be not one-to-one correspondence. So every beam can have different jet. So because when we are converting into, so it depends upon the axis, it depends upon the jet observers. So redshift is also going. So but it is showing the decreasing trend.
And that's, it looks relatively flat as per you
Yeah, so if you
so
see
is
that-
it statistically, is it because there's upper limits?
So
or
in fact,
any
to
other-
check the statistics, we did the simulations as well, like MCMC for individual observation for the RRM, like 10,000 times, the trend still sustained. So it's not just because error bar are like large and so there's no trend. So even in MCMC of 10,000 realization, it was still like this.
Super. Okay, any final questions from the room or online? If not, we can thank Sunil again.